Welcome to the flock. Let's dive into the solubility rules and the formation of precipitates. I'm assuming at some point in your life, y'all have seen a crusty substance on your water faucet or your shower head or your glass shower door. What is that? That, my friends, is a solid precipitate. That is a chemical reaction due to hard water, meaning that there are chemicals in the water that comes out of your faucet at home. And this water has high mineral content like calcium and magnesium, and those precipitate out, forming an insoluble solid that's really difficult to remove on your faucets and your showers and your toilets and pretty much anywhere where water comes in contact with. This is just one example of how precipitates may affect your everyday life. Precipitates occur from a chemical reaction called double replacement. This is when we have two ionic compounds that swap partners, doubly replacing each other on the reactant side. The reactants in this case are always in solution or aqueous. AQ is what we call that. As a reminder, AQ, aqueous, is for anything that's in solution, soluble ionic compounds. We also have G for gas, and the typical gases we encounter are CO2, methane, oxygen, nitrogen, hydrogen, ammonia, and pure liquids, L as a state symbol, water, bromine, mercury, for example, and an S for solids, elements that are by themselves, with the exception of diatomics, of course. So for example, if you were to see Ni for nickel, that would be a solid most likely because that is an element by itself. So going back to this double replacement reaction thing, so if the reactants are always in solution, then the products are typically in solution as well, i.e. dissolved, mixed together, solute and solvent, and floating around in a solution. But sometimes a solid product will literally drop out of the solution, and that solid product is called a precipitate. So for example, if I had calcium chloride reacting with sodium carbonate in solution, hence the AQs after each one of those, they would undergo a double replacement reaction where the cation of one would pair with the anion of the other, and we would end up with the products of calcium carbonate and sodium chloride. Notice that I've written the charges in the upper right-hand corner. We always want to make sure that our charges balance to 0. And if they don't, we apply the drop and swap method. In this case, they all balance, so I don't need to drop and swap. We simply have CaCO3 and NaCl as our products. But NaCl is table salt, and we know that in solution in water, salt dissolves. So that would be aqueous, AQ, in solution. Calcium carbonate, on the other hand, is an example of a precipitate. So this would actually have an S after it for a state symbol because it's actually a solid, just like a rock is a solid, just like a nickel coin is a solid. It literally becomes a solid out of an aqueous solution. And calcium carbonate is just one of the things that you will find plastered to your sink faucets. So then how did I know that calcium carbonate was the solid precipitate that dropped out of the solution? I applied the solubility rules. And really, you should write these down. Things that are always soluble are compounds containing sodium, potassium, rubidium, ammonium, nitrates, and acetates. Remember that the polyatomic ion acetate can be written in two different ways, C2H3O2-1, or CHCO, as I like to call it, CH3COO-1. So literally any compound you encounter that contains these ions in them would always be soluble in solution, no matter what. Then there's this next category of soluble compounds. These are things that are typically soluble but have exceptions. So soluble compounds will contain chlorine, bromine, and iodine unless it happens to be paired with silver, mercury, or lead. So for example, if I had Na paired with Cl, that's soluble. But if I had Pb paired with Cl, it is now insoluble, meaning that it's not going to dissolve in solution. It would be a precipitate. Likewise, if I say had magnesium and I paired that with bromine, that would be soluble, i.e. aqueous, dissolved in solution. However, if I was to take mercury and pair that with the same bromine, it would now become insoluble or a precipitate, not able to dissolve in solution. Soluble compounds can also contain the polyatomic ion sulfate, SO4-2. Those are considered soluble unless the sulfate happens to be paired with strontium, barium, mercury, or lead. So again, I could pair, say, sodium with my sulfate, and that would be soluble. However, if I took barium and I paired it with the sulfate, it would now be insoluble and considered a precipitate. i.e. it wouldn't dissolve in solution. Then of course we have the last category of insoluble compounds. Anything that pretty much contains sulfur or hydroxide is going to be insoluble. Of course there's also exceptions here too. So it's insoluble unless the sulfur or hydroxide happen to be paired with any of the always soluble ions, then it would still be soluble. Or if the sulfur or hydroxide happen to be paired with calcium, barium, or strontium. Any of those three cations would make sulfur and hydroxide soluble as opposed to insoluble. So here, for example, if I was to pair magnesium with hydroxide, that would be insoluble. However, if I was going to take Na from the always soluble list and pair it with hydroxide, it would now be soluble. Insoluble compounds also contain the polyatomic ions carbonate and phosphate. So pretty much anything you pair with carbonate and phosphate will be insoluble, i.e. a precipitate not able to dissolve in solution, unless, of course, the exception being if carbonate or phosphate are paired with an always soluble ion. So for example, I could pair lithium, magnesium, calcium with the carbonate or the phosphate anions, and it would be insoluble. However, if I were to take a sodium or potassium or rubidium and pair that with the carbonate or phosphate anions, I would have something that is now soluble from the always soluble list. I know I've said this a few times, but let's really clarify this. If it's soluble, it dissolves in water. It forms a solution, an aqueous solution, i.e. it has similar or compatible intermolecular forces. Likes dissolve likes. If it's insoluble, it will not dissolve in water. It forms a solid precipitate that drops out of the solution, i.e. it does not have similar or compatible intermolecular forces. Maybe you have something that's polar mixed with something that's nonpolar, like water and oil don't mix. So let's apply the solubility rules to the double replacement reaction we touched base on earlier. If I'm looking at the product side to see which one would be a precipitate, if there is even one, we would first need to check out each atom in this first compound, Na and Cl. If we look over at our solubility rules, we notice that Na is an always soluble cation. Therefore, since Na is present in this compound, this one would have to be aqueous, in solution. Now let's look at our other product, calcium carbonate. We have a calcium and we have a CO3 polyatomic anion. We need to look through our solubility rules to either find calcium or carbonate. Hopefully you see that carbonate is one of our insoluble compounds, and the only thing that would make carbonate soluble or aqueous would be if it was paired with an always soluble ion. Since it's paired with calcium and not any of these that are present up here, we know that this one has to be the precipitate, the solid product. There are many ways to represent the solubility rules, other than how I've presented them. Take a look at this table here, for example. This also includes chromate as one of the ions that form insoluble compounds. My list is by all means not inclusive of everything, but it's in general what you're going to bump into. If you happen to run into something that's not on my list, you can check for a more inclusive solubility rule in an MSDS. Here's another way you can represent your solubility rules. You could pair your anions of interest on one side of a table and your cations on another. Then as you read across the columns and the rows, you can see if something is soluble or insoluble. For example, if I wanted to know if lithium and nitrate together was soluble or insoluble, I would go to the lithium and to the nitrate, go over and down, and I would see that that cation with that anion is soluble. However, if I was going to take that same lithium cation and pair it with a phosphate anion, we would see that that combination would be insoluble. This is just another way for you to help organize the solubility rules. Whatever works for you, use it. Hopefully you wrote down those solubility rules in one way, shape, or form. I'd like you to pause the video here and give this chemical equation a try. See if you can find the precipitate, if there is one, in the products. Ready, go! Hopefully you found that there is indeed a precipitate here. If you were to mix silver nitrate and sodium chloride together in solution, you would have something that looks like this dropping out in a test tube. But what is that white solid that's dropping out of the solution in the test tube? Well, looking at our products, we see we have silver chloride and sodium nitrate. We know that anything that has sodium in it is one of the always soluble ions. So sodium nitrate would have to be in solution, i.e. it would have to be AQ, aqueous. Let's try and find Ag or Cl in our solubility rules list. We see that soluble compounds contain chlorine, Well, wouldn't that mean that AgCl is soluble? Yes, if it were paired with something other than silver. The fact that it's paired with silver is the exception. Even though chlorine is normally a soluble anion, because it's paired with silver, Ag, that makes it insoluble. So in this case, AgCl is our solid precipitate. If you're not a part of the solution, you're a part of the precipitate. Go ahead and give this double replacement reaction a try and see if there is a precipitate in the products or not. Pause the video now. Anything that has sodium in it is going to be an always soluble compound because sodium is an always soluble cation. Therefore, sodium nitrate would have to be AQ, aqueous. It's in solution. But what about the lead-2 iodide? Let's use this other table here to try and figure it out. We're looking for either the cation of lead or the anion of iodine. We see that ions that form soluble compounds include iodine, so it should be soluble, except it happens to be paired with lead, and that would make it insoluble. So here we know that our lead-2 iodide is the solid precipitate product. It's the one that's a part of the precipitate. Before you move on to the next concept, make sure you test yourself before you wreck yourself. Go ahead and see if you can find a precipitate in the products of the following 3 double replacement reactions. In this lesson, we talked about the solubility rules and how to apply them to double replacement reactions. We also saw that the state symbols, aqueous for solution, G for gas, L for pure liquid, and S for solid, apply to each one of the ionic compounds within the double replacement reaction. When we're looking for a precipitate, we always look at the products of the double replacement reaction and apply the solubility rules. If we do happen to find one that's insoluble, i.e. one that does not dissolve in solution, then that would be our S solid product. Whereas the soluble, i.e. the thing that does dissolve in solution, aqueous, would have an AQ after it in the product side. Make sure that you're always a part of the solution and never a part of that precipitate. See you next time.
No ducks, no glory.